In this video, we're going to talk about partial orderings, but first we're going to recall a couple of definitions. Remember that a relation from a set A to a set B is a subset of A cross B. This is the Cartesian product of A and B. So elements in R are ordered pairs AB, where the first coordinate comes from the first set and the second coordinate comes from the second set. And we also use the language that A is related to B. Now, another thing to recall is if you have a relation from a set to itself, so from A to A, then R, the relation, is a subset of A cross A. And we just say that the relation R is a relation on A. And we had these definitions that we used to examine certain properties. They're written here in a couple of different ways using the ordered pair language as well as the ARB language. So take a moment to review these, and then we will talk more about partial orderings, which are a specific type of relation. Alright, so a partial ordering is a specific type of relation that has the properties of being reflexive, antisymmetric, and transitive. Again, this is a relation on one set, A, that we assume is non-empty. And the notation we use for a set that has a partial ordering is this kind of curly equal sign. I'm going to make it a little bigger so you can tell. This is not exactly the same as the typical less than or equal to symbol, so just be careful about that. What we have here is a kind of a more general symbol for what we call a partial ordering. And what we have is that the set A that the relation is defined on, combined with this symbol that's similar to a less than or equal to sign, which we call a partial ordering, these two together define what's a partially ordered set, or PO set. Notice PO is the initials of partially ordered. So PO set is just referring to a set with a relation that is called a partial ordering, and it has the properties of being reflexive, antisymmetric, and transitive. A couple of quick examples. As we mentioned, the symbol for a partial ordering is very similar to the symbol for less than or equal to, and there's a reason for that. The less than or equal to symbol actually defines a partial ordering. We can take a set of numbers. In this example, they're not mentioning the actual set of numbers, but if we just take a set of numbers, we can define a relation using the less than or equal to symbol, and we can verify that that relation is reflexive, antisymmetric, and transitive. So just a quick reminder of how that works. If I have a number A, I know that A is less than or equal to A, so that verifies reflexive. I know if A is less than or equal to B, and B is less than or equal to A, that implies that A equals B, and this is exactly what it means to be anti-symmetric. And finally, just from our experience throughout math, we know that if a number A is less than or equal to a number B, and that number B is less than or equal to some other number C, we can conclude that A is less than or equal to C. And this is exactly satisfying the definition of transitive for a relation. My favorite example of a partial ordering, though, involves what we studied in chapter 5. So one example of a PO set, again partially ordered set, is the set of natural numbers with the divides relation. We can verify that this relation is reflexive, we can verify it's antisymmetric, and we can verify that it's transitive. this example asks an interesting question. It asks, can you explain why z star with the divides relation is not a PO set? Remember that z star is the set of non-zero integers, which means this includes positive integers and negative integers. It just doesn't include 0. So think about why that is, and this hands-on exercise asks you for a counterexample to prove why that's true. And there's a small typo. There should be a star there for when you try this hands-on exercise yourself. So go ahead, pause the video, give this a try. And if you're kind of stuck on this hands-on exercise from the beginning, it might be good as an exercise to verify for yourself that this PO set is actually reflexive, antisymmetric, and transitive. In other words, to show that it is a partial ordering. All right, so we've seen a few examples so far of PO sets. We've seen the set of real numbers, let's say, with the less than or equal to relation. And we've seen the set of natural numbers with the divides relation. I could have also said the set of positive integers with the divides relation as my expression of the PO set. What are some other examples we have? There's one example that involves sets. So let's make up a new example. Let's let cursive P be this set that consists of A, B, C, S, T, U, and V. And let's just say that suppose A, B, C, S, T, U, and V are all subsets of the real numbers. Okay, we have these 7 sets here, and we want to see what relation can we define on them that actually makes it into a partial ordering. So the claim is that P, this set of sets, with the relation subset, is a partial ordering. Okay, so let's prove this. We'll start by letting X be a generic element in this set of sets P, which is why I'm writing a capital X, because capital X is a set that is an element of this set P, which consists of sets. So think back to all the work we did in chapter 4 to understand what sets can possibly look like. It actually makes sense to define a set P where the elements of that set themselves are sets. So I'm picking X to be a generic element of the set P. And what do I know? I know that X is a subset of itself. We can use chapter 4 techniques to verify that. So that shows the relation is reflexive. What about symmetric? If X is a subset of Y and Y is a subset of X, again, I'm pretending Y is a generic element chosen from among these. So if X is a subset of Y and Y is a subset of X, then X equals Y. X and Y are the same set. This is exactly the definition of set equality we talked about in chapter 4. So that proves anti-symmetric. If I said symmetric earlier, I apologize. I meant anti-symmetric. Okay. Finally, transitive. So finally, if x is a subset of y and y is a subset of z, you can imagine that it must be the case, thinking of the Venn diagram, x is a subset of y is a subset of z. Well, we can see here that x has to be a subset of z. And that's exactly what it means to be transitive. So this is a third example of a poset. It's a set of sets, and we're using the subset relation as our relation. I want to start relating this to directed graphs or digraphs. Let's take a finite set of natural numbers. For example, 1, 2, 3, 4, 6, 12. We're going to make the digraph of the poset A with the divides relation. All right. I'm going to make this in a particular way because there's a simplification of this graph we're going to do in a moment. But what I'm going to do is I'm going to start from the bottom and work my way up. So let's say 1 is down here. I'll put 2 here, 3 here, maybe 4 here, 6 here, and I'll put 12 up here. Now let's make the directed graph. Well, we know that this relation is reflexive, which means we know that there's going to be a loop at each point. So if we're going to make the digraph properly, we have to put a loop at every single point. What else do we know? We know that 1 divides 2, 1 divides 4, 1 divides every integer. So I have to draw arrows here for all of them. And then, what else do I have? Well, I know 2 divides 4, 3 divides 6, so I need an edge there. 2 divides 12, 2 also divides 6. I also know 4 divides 12 and 6 divides 12, and I also know that 3 divides 12. As you can see, this is a very messy digraph. There's a lot going on. It's very difficult to read. You can kind of notice some cool patterns, but it's still messy and difficult to look at. We have a bunch of arrows coming out of 1, a bunch of arrows going into 12. This will not necessarily happen with any example of a digraph with divisibility. This is just one particular example. And we have all these loops kind of cluttering, getting in the way. So what can we do to simplify this? Let's take a look at this other version of the same digraph. Let's do a little comparison between these two. What do we notice? Well, the numbers are arranged in a way very similar to how I chose to arrange it. I started from the bottom up. But what else do I see? There's just a lot of nice clean edges. There's no arrows. There's no loops. And we've removed some of the edges. So for example, this edge from 2 to 12 doesn't appear in this graph here. And the reason for that is when we make this simplified version of a digraph, which we call a Haas diagram, what we're doing is we're removing any edges that arise from transitivity. We have a poset, so we already know that this relation is transitive, which means if we have a two-step path from 2 to 12 and a one-step path from 2 to 12, we don't need the one-step path. We have a way to get from 2 to 12. We know it's through 4, and that actually cleans up the graph a lot. And again, as I mentioned, there's no loops at any of these points, and there's no arrows because we have the convention that we're starting from the bottom and working our way up. So moving this messy diagram over here and shrinking down this nicer version, let's investigate what we just talked about. We just talked about what's called a Haas diagram. And so the Haas diagram has us remove all the loops. It has us remove any edges that arise from transitivity. So we don't have the edge from 2 to 12. We don't have the edge from 3 to 12 because we already have a way to get to 12 through 6. And then a lot of the edges from 1 are gone. We only need 2 edges, 1 to 2 and 1 to 3. Because all these other edges are implied by the connections that exist in this graph. So the name for this type of graph is called a Haas diagram. It's a simplified version of the digraph specifically for a partial ordering. Let's do one more example of this type. Let's call this set B. Let's say it consists of 2, 3, 4, 6, 10, 12. When you first make the digraph for this, you might not be sure of exactly how to arrange these numbers, but the general guideline of going from the bottom up is often helpful. So I'm going to put 2 here, 3 here, 4 here, 6 here, maybe I'll put 10 here and 12 up here. So let's see. We're doing again the divides relation. This is our poset. So what's the digraph? Well, the digraph again is going to have these loops, which we're eventually going to erase, but this is good digraph practice because it's a reflexive relation. And we know 2 goes to 4, 2 goes to 6, 3 goes to 6, 6 goes to 12, 3 goes to 12, 4 goes to 12, and 2 goes to 10. Now take a moment to pause the video and decide which of the edges are going to disappear once we make our Haas diagram, this simplified version of a digraph for a partial ordering. Okay, so I'm going to put the points in as close a place as I can that's similar to how I had it in the full digraph. And let's see, okay, all the loops are gone. So what we have over here is the digraph, and now we're about to make the Haas diagram based on that. When you practice enough, you're able to make the Haas diagram without doing the digraph first, but we're just practicing now. All right, so I know I have 2 to 4, 4 to 12. Oh, and I actually, in the digraph, I forgot to put 2 to 12. So there is supposed to be an edge there for the digraph, but in the Haas diagram, we don't need this edge because we have 2 to 4 and then 4 to 12. So I'm just going to draw 2 to 4 and 4 to 12. Remember, we don't need the arrows in the Haas diagram because there's the understanding that we're going from the bottom up. Similarly, we have 3 to 6, 6 to 12, and then we have the 3 to 12, which is an edge that arises from the transitivity property, but we can leave that edge out since we have a way to get to 12 from 3 by going through 6. Now, what else do we have? We have another way to get to 12 from 2. We have 2 to 6 and 6 to 12. Notice 2 to 4, 4 to 12 gives us the 2 to 12 by transitivity. 2 to 6, 6 to 12 also gives us 2 to 12 by transitivity. So this edge here really is not giving us much information because we have two different ways to get the edge 2 to 12 by transitivity. What we want to encode is the different ways to get from 2 to 12. So we have 2 to 4, 4 to 12, we have 2 to 6, and 6 to 12. And then we have one more edge to make. We don't want to leave 10 out of this. Now this isn't the nicest graph in the world because I have some crisscrossing. Maybe I should have put 10 over here or something. But these are the types of things you learn when you make lots of Haas diagrams. I'm going to have you do a lot of practice with Haas diagrams and just play around and see what properties you can come up with. In the meantime, here's one hands-on exercise for you to try. And then there's an additional exercise to have you play around some more with these Haas diagrams.